Hello, and welcome to the Tentative Tutor channel. Can you solve this equation for x and y integers? If you'd like to give the video a pause and think about it, I'll solve this problem in 3, 2, 1. We'll work in the ring of Gaussian integers, z of I, which is all numbers of the form a plus bi, where a and b are real numbers. Keeping in mind that I is the square root of -1, so that I squared is -1. And notice that x squared plus y squared is the product of x plus iy times x minus iy in z of I. These are known as conjugates when we change the sign in front of the I. And also, notice that 1105 is the product of 3 primes, 5 times 13 times 17. We can also write each prime as a unique sum of squares, which we call conjugate pairs in z of I. For example, 5 is 2 squared plus 1 squared, or 4 plus 1, which is 2 plus I times 2 minus I. And similarly, 13 is 3 squared plus 2 squared. Here's how we can multiply out 3 plus 2i times 3 minus 2i, noting that 9 minus 4i squared, since I squared is -1, is actually equal to 9 plus 4. And that's the sum of 2 squares. And similarly, 17 is 4 squared plus 1 squared. So we're trying to find all x and y for which this equation is true. And we already know it's equal to 5 times 13 times 17, and then substituting in our conjugate pairs for 5, 13, and 17, we get a product of 6 elements of z of I, each one and its conjugate pair. So we're going to call 2 plus I P1, and its conjugate 2 minus I will be P1 star. And similarly for 3 plus 2I and 4 plus I. We can easily show that P1, P2, P3, and their conjugates are all primes in z of I. So you have unique factorization, just like with primes in z. And then we can use that to show that the product of 3 of them is x plus iy. And then the other 3 are the conjugates of the first group, and their product must be x minus iy. Let's suppose P1 divides x plus iy. So we can choose one representative from each pair, P2, P2 star, P3, P3 star, to get the other 2 prime divisors of x plus iy. So we get 2 times 2, or 4 possible choices, and that's going to be 4 different representations of 1105 as a sum of 2 squares. Let's look at the choices. P1 times P2 times P3. You can verify if you multiply those out, you're going to get 9 plus 32i, and that's going to be our first answer. And then just taking P1 times P2 times P3 star, the conjugate, we get a different one, 23 plus 24i, and so forth for all 4 combinations. So this gives us 4 different ways to factor 1105 in terms of x and y. That will lead us to 4 distinct sums of squares. The first one being 9 plus 32i times 9 minus 32i. Those conjugate pairs in z of I gives us 9 squared plus 32 squared. So 9 is x and 32 is y. And the next one, 23 will be x and 24 will be y. And then 2 more. And all of these are sums of squares that add to 1105. And this is the complete list. See if you can verify. And I would challenge you to find any more. Now here's a homework problem. See if you can solve this one using the same methods. Notice that I merely took 1105 and multiplied it by 5. Now here's our bonus problem. Find all integers x, y, and z for which the sum of these cubes is equal to 4549. Be careful, there's a twist to it. Leave your answer in the comments. And once again, thanks for watching.